Hi, can everyone hear me?
Yeah.
Cool. All right. So this is a talk about machine learning with Scala. So I'm a senior developer at Scott Logic. I got interested in data when I was doing my master's, and currently I'm doing a data-related project for a client, and I just try various things at times because it's a fast-moving field and quite hard to keep up. So today I'll be talking about machine learning and Spark, Scala, and maybe some more. So some of the typical machine learning systems, these are. And I think fraud and sales recommendation are quite widely implemented now in industry. Image classification is slightly more novelty still, but I think some of the big players are doing quite amazing stuff with that. For example, a few months ago, Google had something on their page where you could draw up something and they would be able to tell what it is you have drawn. But yeah, there are other usage of that as well. So to give a bit of context, I used to work for a loan company. So it's a peer-to-peer finance alternative finance company. And we used to get lots of fraudulent application. Kind of similar to what Chris mentioned for nexmo. But I think ours was more in the face is that they're wanting to take money and then they would just never pay it back. So we had to do something about it because although we had some protection and lots of manual observation, it would be good to have a system that can flag up any fraudulent application by looking at their details. So the overall architecture, it has a few different modules. So the bulk loader, the CSV has gone a bit funny. Anyway, so that kind of reads the data from CSV and loads into Cassandra. It's written in Scala and Spark. And then the model builder is kind of separate from that. That would read the data from Cassandra and train it and store the model somewhere. And then the request sender stuff kind of works separately. That's for kind of the real-time application. It will receive and then store in a message queue. And then the request processor, so yeah, let me finish the sentence. So it will read the message or the loan application that has arrived in message queue and just load the model that has been saved previously by the model builder and then predict whether it has a possibility of being fraud or not. So that's kind of the overall architecture. And I chose Scala because at the time I was very keen on Spark. I'm still very keen on Spark, and because of the distributed engine, obviously, and fast processing. And I think the two APIs that Spark had at the time, and still has, Scala and Python. Scala was a more efficient one, so decided to go with Scala. And so the steps I went through, so I did my initial analysis on 3 years data using R. So I cleaned and prepared the data in R. I know that Chris made some comments about R, but anyway, that was the data analysis language I knew at the time. So that was kind of the initial analysis and trying out various different algorithms. I tried, I think, generalized linear regression and support vector meshing and also random forest. So I ended up using random forest because that gave the best accuracy and without sacrificing speed. Because I think support vector meshing and random forest came up with similar accuracy, but support vector meshing was taking much longer. I didn't do a lot of feature engineering. I was mainly using the data that was available quite readily, the data that we capture about each loan application. Yeah. And then I did a production-ready implementation in Scala and Spark, and did a initial deployment in Docker and then in Azure. So to have a closer look at the Spark implementation, we had the, so I used Spark's Spark ML API, which is Spark's machine learning API. So it only came out at the time when I was doing it. Previously, it was MLlib. The good thing, so MLlib was deprecated after ML came out. Although still you can use it, but I think the reason I chose ML is that you can have a whole pipeline. So MLlib didn't really have any option of that. So you can chain all your steps of cleaning and preparing data and then store it as a model. So here the stages that I'm doing is there's a string indexer, which kind of takes your categorical columns that are string type and indexes them into string, indexes them into ints. So that's good for efficient processing, and also, and then the next step is a one-hot encoder, which takes the integer categories, and then what it does, it assigns a bit for each category, and that way, so instead of having integer representing each category, you're having a bit representing each category, so that's more succinct as a representation. And then the vector assembler would take all your one-hot encoded columns and assemble them into one vector. And then we're doing a vector indexing again to make it more, so it's similar to string indexing, because once you do the vector assembly, you're probably getting a very wide vector, and you don't necessarily need that wide vector to represent each of the categories distinctly. So vector indexer does that. And a label indexer does something similar, but the difference is the first 4 steps would work on the input features, so the user's properties that we are taking in this case, or the loan application's properties. Whereas the label indexer does the indexing for the output feature or the target column, which is the classification of fraud. And once you have done those kind of transformations, you can run the random forest classifier. So this was quite interesting, because when I did the initial analysis in R, I had to kind of hand code each of these transformations, because the algorithm requires them in that, requires the data in that format. But when I did it in Spark, it was all out of the box. Spark ML provides functionalities for doing each of these things. You just point the functions to your columns that I want this column to go through these kind of transformations, and it does it. So after we run the data through these transformations, the input, after we run the input data through the first 4 stages, we then split it into the training and test data. So the training data is the data we run through the pipeline to come up with our parameters. And then we use the test data to kind of validate how much, how good the model is. So that's what is happening in the, when I'm doing the transform test data thing. And then I run an evaluator to see how it is doing across each class of fraud, because I had 4 different types of fraudulent applications. Perhaps I should point it out that my initial data set was, I think I mentioned, it was 3 years data, because we had 3 years history of loan applications, and we stored which one of them were fraud or not. So we had the data available. So this is also some more code. I won't go to the detail of this. So this is the receiver bit, which reads from the Kafka message queue and invokes the model that was previously stored, and uses it to predict whether the application details it read from the message queue is fraud or not. So that's quite good, as in I had a system and it works, quite efficient. So why, what's new or what has changed? So when I was working on the system, I wasn't very aware of deep learning, because it wasn't very common at the time, kind of novelty. But I think over the last couple of years or more, it's getting more and more widely used in the industry. So if now I went to go and build a similar system, I would definitely want to have some sort of deep learning in my system. So deep learning has been around for, the concept has been around for many years, probably from, not deep learning, the neural network concept has been around since 1960s. But I think the reason it became quite important in the recent years is because we started using GPUs in calculation by neural networks, and therefore we can now process amounts of data that we couldn't previously even imagine. So that's two things. We have cheap commodity GPUs and loads of data that we didn't have before. But is deep learning always good, or when would you actually use deep learning? Because like I mentioned, I already had a system and it works. So I think it depends on your use case. Say when I'm doing the fraud detection, I was probably using in the initial stage like 20 features. When another data scientist in our company kind of took it over and did more feature engineering, he was probably using like a few hundred features. But say that's one type of problem. But if you look at image classification, you can have thousands of pixels or even more. And then you're trying to classify using all those pixels. So that's kind of the scale of problem we're looking at. So that's, so you'll have to have really complex problem. And then you also need to consider that it does take longer to train a deep learning model compared to other models, compared to traditional machine learning models. And you also have to invest into infrastructure. So having said that, say we still want to do deep learning because it's just new and cool. And obviously one of the newer APIs is TensorFlow. And it has 4 languages supported. It has APIs in 4 different languages, but unfortunately none other than Python is actually supported by stability promise. And obviously there is no Spark support. But it would be, I mean, why would it be good to have deep learning and Spark in the same infrastructure? Because say you already have a Spark cluster and you want to do deep learning. And if you want to do that in a distributed way, TensorFlow does support it, or other frameworks do support it, but you will need to maintain 2 different clusters. And also, say you're keeping your data in one of the clusters, then you have the job to transfer it into your Spark cluster as well for productionization. So we want to stay in Spark and JVM, and we also want to do deep learning. So what are the options? So one of the frameworks that kind of have been around for a while is SparkNet, and it's a wrapper on Spark and Caffe. Is written in C++. So it works by model parallelization, whereas it sends the model parameters into each of the worker nodes from the master. So it is good, but the problem is it's only supporting Caffe. So that's a limitation. You can't do TensorFlow or any of the other type of models. And then there is deep learning for J, which supports both Scala and Java, and it actually primarily supports Java and Scala. So it's the first dedicated deep learning framework for Java and Scala. I guess the reason it didn't quite gain much uptake because although it's open source and you can do a lot of things by yourself, if you want to do more sophisticated stuff, you'll probably have to seek help from their commercial support arm, which is SkyMind. And then early 2016 came on Caffe on Spark, which was released by Yahoo. And so Yahoo internally uses Caffe quite a lot for their deep learning stuff. And they decided that they want to have basically Caffe and Spark in the same infrastructure. So that's why they developed it, and they made it open source, but still only Caffe. And then there's Stencil Frames, which is developed by Databricks, which is the company that kind of builds and supports Spark. But TensorFlow is, Stencil Frames is cool, but the problem is that they're quite low level, and it's mainly targeted for applying TensorFlow calculations on Spark data frames, which makes sense because you have to look what is Spark good for and what is TensorFlow good for. So Spark, if you're using Spark SQL, you have the catalyst optimizer. If you have a process that has many stages, your optimizer will mesh those stages and find out the fastest processing steps for you. So it's good when you have a process that has many stages. It is not necessarily very good when you have a process that's only one stage, but quite sophisticated mathematical calculation. TensorFlow is good for that, like really complicated numerical calculation. So if you could have those two abilities together, you can have a very efficient system. So that's where you'd probably use Stencil Frames, but as it is quite low level, trying to implement deep learning using Stencil Frames would be near to, if not impossible, it's a lot of work, because you'll have to code each of your layers by hand, basically. And then there is TensorFlow on Spark, which is again released by Yahoo, which is early February 2017. And the problem is it's a Python API, and it's only targeted for PySpark, and there is no JVM support. But so far, it's probably the most mature API that you have for doing deep learning on Spark. And then we have BigDeal, which is again, API released by Intel, and it also came about the same time as TensorFlow on Spark. So you can integrate Caffe or TensorFlow models on it, or you can create your own models. That's possible, and they have both Python and Scala APIs. So these are kind of the major players, and I'm sure there are more. If you keep looking, there you will find more. Like when I was Googling, I found a few that were developed by individuals or companies that wanted to have a system that will serve deep learning models in Spark. So quite a lot of options, but I don't think you can point out one of them that are very good or very mature right now. They're all kind of evolving, so you just have to make a choice and go with one. But these are kind of things that you can think about if you want to do deep learning in JVM and Spark. These are the options. Obviously not taking into account the cloud-based ones that kind of Chris presented. So that's also an option. So we'll have a look at some sample code. So how hard it is or how different it is to do a deep learning system in JVM from doing a traditional machine learning system. All right. I'm not too sure how, I can't really scroll through it quickly.
Control plus.
I think this one will do. It's fine, it's fine.
Sure.
So BigDeal has this concept of engine that you have to initialize with your Spark configuration. And before you do any kind of data processing, you have to call the engine.init. And then I'm just reading some data, some credit card data, using the data frame API. And these are just usual kind of tweaking some values, because I don't want them to be, so I want to kind of, I want the algorithm to perform efficiently. So after doing all that, so this data is much simpler than the data I used for the system I showed earlier, because this is more of a sample data set for credit cards, because it would be quite, I mean, if I wanted to do the demo using the whole loan applications data set, that would be quite complicated. So I'm going with a sample data set instead. So after doing the tweaking bits, I'm just splitting the data into training and test. So up to this point, I'm actually doing standard Spark stuff, like data frame stuff. Nothing much big deal related, other than the initialization. And then I'm doing some normalization, which is also Spark and data frame stuff. And then I'm doing some shuffling of the data, because I don't want them to be all grouped in one place. And then splitting the set, test set into validation set and test set. And then this is kind of the BigDeal stuff, because BigDeal expects the data in a sample data type, which is a set of tensors. So you will have a tensor for your feature sets and a tensor for your target column. So doing kind of similar thing for both for training set, test set, and validation set. Should really extract that into a function, but anyways, kind of quickly put together demo. And then I'm specifying my hyperparameters, and then kind of defining the model. It's a very simple one, as in I'm only using very simple components. So a few linear regression layers and a dropout, another linear regression layer, and a softmax. And then it takes you have to define an optimizer for the training thing to work, because it needs to know what it is trying to optimize. So I gave the MSE criterion, which is mean squared error. So at each epoch, it will check how it is doing in terms of the target column and what it is found so far. And then you're just calling optimize on the optimizer. Afterwards, I'm just doing some filtering. No, sorry. So I'm running the test data through prediction, and then checking how it is doing in terms of each class. So that's what it is. So what it looks like up to kind of cleaning and preparing data. You can use your usual Spark and data frame stuff, and you could probably even store them as a Spark ML pipeline and load them up, so you don't have to have it all in one application. And afterwards, it's just when you're going to do your prediction, model training and prediction, that's when you do the BigDeal thing. And it's completely pluggable within your Spark application. So it will work in a distributed way, like Spark works. All right, so I think that was my talk. Does anyone have any questions? All right.
So with
yes.
If you were to do the same thing again, knowing what you now know,
Yes.
what's probably some of the something that you're particularly aware, you're like, oh, we in hindsight we could have done it differently, and now we've learned more, and we could have, you know, what's something like that?
I would probably leave doing deep learning until it matures more, especially if I'm doing on-premise and not using the cloud vendors. Because I think it is cool, but I think with these problems, we can already do quite well, so probably don't need deep learning yet.
Are you guys running that on-premise or in the cloud, the original system?
So the code was hosted on Azure, but what I meant by on-premise is that the machine learning algorithms, they're all written in your environment. We're not calling any vendor APIs or anything.